Okay, in this video, we're finally going to bring truth into it and talk about truth tables. So this is like the semantics of propositional logic. What are the meaning of these symbols and how do we track the meaning as they become complex formulas? This will be the longest video this week because there's about 10 slides we have to cover. So we can track and calculate the truth of well-formed formulas using something called a truth table. And what a truth table does is it takes a list of all the different possible situations or truth configurations to check whether or not a WOOF is true or false. So let's look at a small beginning of a truth table here. So this is how we can set it up. Let's say we have two well-formed formulas, alpha and beta. We want a truth table that contains all possible combinations of truth. It's kind of like building a power set in a way. So what we do is we put our propositions on the top of each column. So alpha and beta, that heads, that's what we're looking at in that column. And then we have different possible combinations. So in our first line, we have alpha is true and beta is true. So remember, true is represented by ones and false is represented by zeros. So our first line says alpha's 1, beta's 1, so that means they're both true. In the second line, we're saying we want a combination where alpha is true and beta is false. So that gives us a line 1, 0, where alpha is 1, beta is 0, because alpha is true and beta is false. In the third line, we have alpha false, beta true. So alpha false gives us alpha 0, and beta true gives us beta 1. And then in the last situation, they're both false. Alpha's false, beta's false. That gives us a 0 and a 0 in that row. So this gives us all different possible combinations of truth. So a world where alpha and beta are both true, a world where alpha and beta are both false, and a world where only one of alpha beta is true and the other is false. So depending on how many different atomic statements or atomic propositions we have, remember these are just single things on their own like alpha, beta, p, q. Depending on how many there are, you have different amounts of rows. So if you have just one thing, you only need 2 rows. You need a row where alpha is true and a row where alpha is false. If you have 2 propositions, you need 4 rows because you need alpha true, alpha false, beta true, beta false, and all combinations. So it's just a power. So 2 to the 1 gives us 2 because there's one proposition. 2 to the 2 gives us 4 if there's 2 propositions. If we have 3 atomic statements or 3 propositions, then we're going to need 2 to the 3, which gives us 8 rows. So the most you'll ever need to do is usually 8 rows for me. Once you get to 4 or 5 statements, usually the truth table gets too big to worry about doing a full truth table. To state whether a proposition is true or false, so let's say the value of alpha is true, we write alpha in these double brackets, and we write either 1 or 0 after the equal. And this just means that alpha is true. If alpha was false, we could write alpha in our double brackets, and we could write that equals 0. And that would mean that alpha is false. Some other ways you might see this written elsewhere are things like the value of alpha is equal to 1, or sometimes it's just v of alpha equals 1. You can choose whatever method you want. However, I definitely recommend using this because when we get to our semantic trees for actual sentences, that's the notation that we use. So we're going to talk about how these different operators change our truth table. So we'll sort of talk about translation at the same time, but not too in-depth. We'll just give some English equivalents. So the first one is negation. So this is the not symbol. You might also see this written as a squiggle in some books. So this is equivalent to the word not in English, or it is not the case that. And typically we use the word it is not the case that because that always appears at the beginning of a sentence, and that means it's unambiguous. Like the every flat earther did not believe the evidence. That gives rise to scope ambiguity when you just use not on its own. So for a lot of cases, we use the full sentence, it is not the case that, or the full clause. So the way that the negation works is the negation just flips the truth value. So it says that for any WOOF alpha in propositional logic, not alpha is 1 if and only if alpha is 0. So that also means that not alpha is 0 when alpha is 1. So in other words, here's the truth table for it. If alpha is true, this means with 1, that means that not alpha is false. So I think I might actually just draw these at the same time on the left with some colors. So if alpha is true, that means not alpha is false. If alpha is false, this means not alpha is true. Because this is like saying not, right? I am happy. If that's true, then I am not happy is false. I am sad. If that's false, then I am not sad is true. So here's the situation. Let's say Josephine is awake. Let's call this P, capital P, because it's a specified well-formed formula, and we're saying that's false. So Josephine is awake is false. That means that Josephine is not awake, or in other words, not P, is true. Because if she's not awake, that means that she's sleeping. So is not awake would be the same thing as saying she's sleeping. Or maybe that means she's unconscious or something. So that's a real example with the negation. Another way, of course, saying Josephine is not awake is to say, it is not the case that Josephine is awake. That'd be another way of paraphrasing that. Okay, so that's the negation. And negation only attaches to one thing, so all it does is it flips the truth value. The conjunction. These are words like and, but, although, even though, anything that has this and meaning towards it. So this requires two well-formed formulas, alpha and beta. So we're going to have a column for alpha, a column for beta, and then we're going to have a column where we take the conjunction. So I do like using colors for these ones and zeros because it just really highlights how these rules work. So alpha and beta is true. So in other words, both of those things are true if each individual well-formed formula is true. So alpha and beta is true if and only if alpha is true and beta is true. Everywhere else, it's false. So in our truth table here, if alpha is true and beta is true, then yeah, alpha and beta is true together. But in every other case, so alpha is true, beta is false, but one of those is false, so the entire conjunction is false. In the third row, alpha is false, beta is true. Oh, that comes out as false because alpha is false. They both have to be true. And in the final row, both of them are false, so of course the conjunction of the two is false. So that is what our truth table looks like for alpha and beta. So imagine a situation where Josephine is sleeping and Brett is humming. So Josephine is sleeping, that's true. Brett is humming, that's true. Therefore, I can say Josephine is sleeping and Brett is humming is true. But imagine if Josephine was not sleeping. Well, then if I said Josephine is sleeping and Brett is humming, well, that would be false, because Josephine would then not be sleeping. So alpha and beta, this is true only when both alpha and beta are both true individually. So a little bit of comments about words like but and although. Sometimes when you have a word and we listen to and, there's this notion of time. So sequential events. And I give two examples here because these really, really evoke these. Megan got married and got pregnant. There's sort of this implication here that marriage happened first, and then second was pregnant here. So Megan got married and then got pregnant. That's sort of the implication. Compare it with B. Megan got pregnant and got married. Megan got pregnant and got married. There's this sort of implication here that Megan got pregnant and then got married. Now, when we translate logic, or English sentences into our logic, we don't deal with this temporal ordering. This is just an implication. It's not an entailment, so we don't translate ordering. So we just translate and as and there's no assumption about which events come first. There's some other conjunctions like the words but and even though. These have contrast meanings or unexpected meanings. So for instance, Jane snores, but John sleeps well. Oh, that's surprising because Jane is snoring, so someone normally wouldn't sleep well, but John happens to sleep well. Or even though Jane snores, John sleeps well. It's the same type of meaning, but we use even though here. So we don't translate contrast either. These are just considered variants of and. And we have to think about the meaning. So Jane snores, but John sleeps well. What is that in terms of facts? Well, it's a fact that Jane snores. It's a fact that John sleeps well. So both of those things are true. It's analogous to John snores and John sleeps well. Sorry, Jane snores and John sleeps well. So we have to remove meaning of contrast and we have to think about, do these words mean and? Generally, there's a little tip. Most conjunction categories mean and. Most of them do. So, yet, so. Really any of the fanboys and your conjunctions there. Fanboys, for and. For and. Okay, this is a little bit embarrassing. I've forgotten the and in fanboys, but there are 7 conjunctions used by fanboys. So, but, not or, and then there's yet and so. So those usually have an and meaning. I think the nor is the and. So nor and or are a little bit different, but the other ones are definitely ands. So all this extra meaning we don't translate. We just consider it and, we give it that meaning, and then we move on. So the next one is disjunction, specifically inclusive or. So these are words like or and unless. So if you have 2 well-formed formulas, alpha and beta, and you can make the operator alpha or beta. So if we set this truth table up, 1, 1, 0, 0, again with our green and red. Okay, so alpha or beta is true if either alpha is true or beta is true or both are true. So alpha or beta is only false when alpha is false and beta is false. So in the first row, alpha, beta are both true, so alpha or beta is true. In the second row, alpha is true, beta is false, but alpha is true, so at least one of them is true, therefore alpha or beta is true. In the third row, alpha is false, but beta is true, so at least one of those are true, so alpha or beta is true. In the last row, though, alpha and beta are both false, so neither alpha nor beta are true, so alpha or beta is false. So the only situation for or that is false is that final row. So imagine we have a situation where Josephine is sleeping and Jack is also sleeping. So if I say Josephine is sleeping, that's true. If I say Jack is eating, okay, that's false because Jack is sleeping. So when I conjoin these, and I say Josephine is sleeping or Jack is eating, well, yeah, the first one's true, the second one's false, but at least one of those is true, therefore the or statement is true. Josephine is sleeping or Jack is eating. Okay, so that's inclusive or. And what I want to say is all or in English is inclusive. Is inclusive, okay, what I should say, we treat all ors in English as inclusive for translation. There's one exception which we're going to see in a bit, and I'll cover it then, but just for now, whenever you think of or, this is inclusive. So you can think of it as if alpha is true and beta is true, then alpha or beta is true because at least one of those is true. And that's how we treat most things in English. The exclusivity, where you think, oh, well, if both are true, then the or isn't true. That exclusivity is an implicature, and we'll talk about it in a bit, as in right now. So this is the exclusive or. This is when you say alpha or beta, or A or B, but not both. So exclusivity is an implicature. So this but not both is explicitly stating exclusivity. When you explicitly state exclusivity, we have a new operator. So how this one works is this says alpha exclusive or beta is true if alpha and beta do not have the same value. So I'll fill in a truth table for this. So it's true, alpha exclusive or beta is true when the values are different. So in the first row, alpha and beta are both true, so alpha exclusive or beta is false. In the second and third row, well, second row only alpha is true, so the exclusivity is true. In the third row, only beta is true, so the exclusivity is true. And then in the final row, they're both false, so we end up with a false for exclusivity. So the example here, which you might hear in a restaurant. All entrees are served with soup or salad. Now, there is an implication here. The implication is that you can have soup or salad. I can write that a little bit better. Soup or salad, but not both. That is the implication. However, you don't know for certain because you might ask and you might say, can I have both? Or does it cost more to have both? You can always ask that question. So because you have to ask that question to see if you cannot have both or you can have both, that implies it's an implication. So in order to actually use this operator for exclusive or, you have to see but not both explicitly stated. And for that purpose, in this course, we will almost never see exclusive or. Almost everything that we deal with in this course is going to be the inclusive or. So that's what we're going to see for almost every or that we see. If we do use exclusive or, I will explicitly state that we are using exclusive or. So please keep that in mind. If you look at a sentence and you think, this might be exclusive. Remember, that's an implication. We're not translating the implication. We're just translating the sentence on its own. We're translating that entailment, if you will. So we're going to talk about this a little bit more at the end of the course, perhaps in the pragmatics and jokes lecture, but maybe not. We'll see how time permits, and we'll see how exhausted we are at the end. Okay, there's two more truth tables to cover. This one is the conditional, and this one conceptually is the most difficult to wrap our minds around because even in psychology, we've learned that we don't like conditionals very much as humans. We're really bad with dealing with them. So, this is an if-then statement. So, if alpha, then beta, and we have some terms to cover. The thing on the left side of the arrow is called the antecedent. You can also think of this as being the condition. So the antecedent says if alpha occurs, if this condition is met, then what do we get? So beta on the right side is what's called the consequent. So this is the then that happens. So this is what happens when the condition's met. So if alpha happens, then beta happens. So with this in mind, let's think about the truth table for this. So I'm going to draw this out. So the way that this works is we say that alpha arrow beta is true if alpha's false or beta's true. So one of those two things. So in the first line, well, beta is true. So alpha arrow beta is true. In the second line, alpha is true, so alpha is not false, and beta is false, so beta is not true. So neither of the conditions are met. Therefore, alpha arrow beta is false. In the third and fourth row, well, alpha is false, so that meets one of the conditions. Therefore, the last two lines are both true. So intuitively, this isn't really intuitive, but I like to give you an intuitive analog. It is, so alpha arrow beta is false when you lie. That's when it's false. Any other time it's true. So what do I mean when I say you lie? If I say, for instance, maybe I should type this one out. Where can I put this? Let's put this here. Okay. If you eat dinner, you will eat dessert. Okay. Let's think about this sentence. So let's imagine I eat dinner. It's saying if I eat dinner, I will eat dessert. So I am lying to you if you eat dinner and then I say you cannot have dessert. So that would be a lie, right? I'm saying you ate dinner and you did not eat dessert. There's a lie right there. Because if you eat dinner, what should happen is you should be eating dessert. So if you eat dinner and then you get dessert, it's true. If you eat dinner, but then you don't get dessert, that's false because essentially I've lied to you here. Now, imagine I don't eat dinner at all. So if I don't eat dinner and I don't eat dessert, that's expected, whatever. We'll say it's true because I have not lied to you. But if you don't eat dinner, what's stopping you from eating dessert? That's okay too. It doesn't say what happens when you don't eat dinner. It just says what happens when you do eat dinner. So, regardless of so if you don't eat dinner at all, we say the conditional is true because I haven't lied to you. So this is sort of how I like to think about it, because the conditional on its own, usually you take a look at these last two lines with your intuition and you think, hold on a second, this doesn't make sense. Because this happens all the time in real life. Well, you didn't eat dinner, so you don't get dessert. Well, no, that's not correct logic, because you only said if you eat dinner, you get dessert. But if you don't eat dinner, you can still have dessert because there was no specification for what happens when you don't eat dinner. So if that works for you, great. If not, you can always just remember the definition here and go by that. That's another way of doing it if that intuition doesn't help out so much. So imagine I have a situation where it's raining, but it's not wet. So it's raining, that's true. It's wet, that's false. And I'm saying if it's raining, then it's wet outside. So uh, if it rains outside, but then it's not wet outside, okay, I've lied to you, so this comes out to be false. Because if it is raining, then it should be wet outside because the antecedent, because the condition has been met. Therefore, the consequence should be borne out of the condition being met. So that's the conditional. And here's another slide just about that point about when the antecedent is false. When the antecedent is false, the entire conditional statement's true, and we don't care about the consequence. So even with this absurd example, if Danny DeVito wins the presidency in 2020, dolphins will take over the world. Okay, if this does not happen, the conditional is still true. Still true. Still true. So even if that's false, the conditional is still true, and that's because we can't test it. We can't test it. We can't see if we're lying or not. So that's how we can think about it in terms of being true overall, as long as that antecedent is false. So the last connective we have is the biconditional. So this is a if B with two F's, and that means if and only if B. So this just means that we have alpha arrow beta, and we have beta arrow alpha. So in other words, it's in both directions. So if is one direction, only if is the other direction. So if and only if means both directions. And in English, we can think of this as A is the same as B. So if we have two well-formed formulas, alpha, beta, we get alpha if and only if beta. This is going to be true if the values of alpha and beta are exactly the same. So if the value of alpha is equal to the value of beta. So in the first row, alpha and beta are both true. So alpha if and only if beta is true. In the second and third rows, alpha is true, but beta is false. Oh, different values, it's false. A third row, alpha is false, beta is true, different values is false. Last row, alpha and beta are both false. Therefore, alpha if and only if beta is true. So this is also like saying it's the opposite of alpha exclusive or beta. It's the opposite of that. So another way you can check is just by taking the values of both, but this is basically the if and only if truth table. Another way of thinking about this is just thinking about vice versa. So if A is true, then B is true, and vice versa. Or if A is false, then B is false, and vice versa. That's another way of translating this. So those are all the connections we have. So I want to show you how to build truth tables. And here I have a nice little translation. So the sentence I have is, if Prancer and Donner fly away, Cupid will be alone. And I've given each one of these little sentences propositions a letter. So P is for Prancer flies away, D is for Donner flies away, and C is for Cupid will be alone. So I've translated this into a formula, P and D arrow C, and I've shown the syntactic structure for this. So I'm going to build the truth tables by filling these out. So I want all different combinations of truth. So there's sort of a little strategy for how I build these. With the rightmost atomic proposition, I alternate 1, 0, 1, 0, 1, 0. I go left one, I double up, so 1, 1, 0, 0, 1, 1, 0, 0. I go left one more, and then I double up on that again, so 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0. So when I build a truth table, I need to track the propositions as they get built. So I have P, D, and C right now, but I have to build P and D. So I need to know P and D both to get the truth value of P and D. In order to get the truth value of P and D arrow C, I need to know the truth of P and D, and I need to know the truth of C. So basically, each one of these columns is a different step in our syntactic tree. So first, I need to know what P and D are. So I need to take the value from P, the value from D, and see what P and D is. So remember, P and D is true. So and is true if alpha is true and beta is true. So in the first row, P and D are both true, so P and D is true. Second row, P is true, D is true, so P and D is true. In the third and fourth row, D is false. So at least one of those is false, so P and D is false. In the 5th, 6th, 7th, and 8th row, P is false in all of those. So the conjunction of P and D will be false as well because we need both of those things to be true. So our column for P and D tracking its truth is 1, 1 in the first two situations and false in all the rest. Now, P and D arrow C, I need to consider the values from P and D to C. So really what I'm doing is I'm comparing these two, and I'm doing it backwards. So P and D is our antecedent, C is our consequence. So remember, alpha arrow beta is false if alpha is true and beta is false. It's going to be true every other case. So for P and D arrow C, I'm actually on the left side, I'm going to write out what the values are. So P and D arrow C, I have 1 arrow 1. In the second row, I have 1 arrow 0 because I have P and D going to 0. In the third row, I have 0 arrow 1. Fourth is 0 arrow 0. And then for the rest of these, I'm just going to get 0, 1, 0 arrow 1, 0 arrow 0, 0 arrow 1, and 0 arrow 0. Okay, so in this case, it's false in the second row because we have 1 arrow 0. And in all of the remaining rows, it is going to be true because either the antecedent is false, meaning 0 is on the left, or we have 1 arrow 1. So this final column here is the truth of the complex well-formed formula. So if Prancer and Donner flies away, Cupid will be alone. What this means is that it's only false when Prancer flies away, Donner flies away, and Cupid is not alone. So that's the condition where this is false. So you look at the individual values to figure out which sentences are true, which sentences are false, and that tells you when the entire complex sentence is false. Okay, I'd like you to try this on your own. So this well-formed formula has no meaning whatsoever, but you can draw its syntactic tree and then try to build its truth table. So pause the video, try it yourself, and I'll go over the answers now. So first, I want to build the syntactic tree for it to figure out what we have to build for our truth table. And when you get good at this, you don't have to draw the tree at all. But just to illustrate now, P and Q is on its own, OR is on its own, and then not Q arrow P becomes its own well-formed formula. So P and Q we can split into P and Q. Not Q arrow P, we can split to not Q arrow P. And then not Q, we can split into not and Q. So when I'm building my truth table, I need a column for the P's. I need a column for Q's. Then I need a column for not Q. To build not Q arrow P, I need a column for that. I need a column for P and Q. And I need a column for P and Q or not Q arrow P. So I actually need quite a few columns here. So because of that, I'm going to shrink this a little bit. And I'm going to do some behind the scenes stuff to set this up to make it look a little bit nicer. So I need a column for P. I need a column for Q. I need a column for not Q. I need a column for not Q arrow P. I need a column for P and Q. And I'm going to abbreviate things a little bit by calling that 1 and 2, and then making a column for 2 or 1. So that's just a little shortcut for what we did. And then I'm going to set up this truth table. So 1, 1, 0, 0 for P, and 1, 0, 1, 0 for Q, and now I'm going to take away the lines. Okay. So for not Q, we're just taking the opposite value of Q. So whatever Q is, we flip it to get not Q. So all of the true Q's are going to become false for not Q, and all of the zeros are going to become ones for not Q. So we can see a conversion side by side here. So now we've built up this information for not Q. So now we can do not Q arrow P. So we're going from not Q to P. So the first row is going to be 0 to 1. So 0 to 1 is true. In the second row, we're going to have 1 to 1. That is also true, because not Q is 1 and P is 1. In the third row, we're going to have 0 to 0. So not Q is false, P is false, so that's going to be true. 0 arrow 0 is true. But in this last row, we're going to have 1 arrow 0. So 1 going to 0, and that's going to be the case where it's false, because not Q is true and P is false. So that is 1 to 0. Okay, so now we've done not Q arrow P. We now need to do P and Q. So remember, P and Q is true when both P is true and Q is true. So that's going to be true in the first row. Taking a look at these two columns, in the second, third, and fourth row, at least one of those is false. So P and Q will be false in those rows. Now, for the final one, we're comparing P and Q or not P arrow Q. So we're comparing these two. So remember, or just means at least one of those has to be true. So in the first row, they're both true, we're good. In the second row and third row, not Q arrow P is true. So of course the disjunction is true. But in that fourth row, both of those are false, therefore not Q arrow P, P arrow Q, they're both false. So the or between them is going to be false as well. So that's it for truth tables. A little bit of a long video. We covered quite a bit there in terms of how to draw the trees, how to draw truth tables, looking at them individually. In the next video, we're going to learn how to translate sentences into propositional logic. But for now, if you have any questions, as always, discussion board, email, I'll get to you when I can.